Okay.
It's my great pleasure to introduce our speaker today. He's very well known to many of us, but anyway, Juan Pablo Rincón-Zapatero. Juan Pablo is professor at Universidad Carlos III de Madrid. He is interested in many areas, including macrodynamics, dynamic games, insurance, and finance. His work appeared in top journals, including Econometrica, Journal of Economic Theory, European Journal of Operational Research, and I stop enumerating here. Thank you very much, Juan Pablo, for accepting the invitation, and the floor is yours.
Yeah, thank you very much for your presentation, kind presentation. Okay, this is a work that was already presented in past 2025 in Paris. Here I have not updated the date, but in fact I have included more results on the previous talk. So, and this is about the characterization of non-smooth and discontinuous Markov Perfect Nash Equilibrium in differential games. And here this has two parts. The main part is a theoretical one in terms of given sufficient conditions for characterizing this kind of Nash equilibrium. And then I have an application to resource games, non-renewable resource games in a very easy fashion. So this is the more schematic game. So I try to show the characteristics of this kind of solutions and how we can manage them. So let me go to the second slide. So we analyze in a player. This is the theory, right? Then the applications, I focus in a much more restricted class of games. And in player, non-cooperative differential game with finite horizon. So I disregard from this analysis the infinite horizon case. And we work with the Markov Perfect Nash Equilibrium. So we use feedback strategies that depend both on time and the state variable. So here, as you well know, characterizing Nash equilibrium in this context is difficult because in general we have to work with partial differential equations. The usual thing is to work with the Hamilton-Jacobi-Bellman equation that is highly nonlinear, because after we perform the maximization that is in the definition of the equation, then we have in general that the equation is not linear in the first order derivatives of the value function. As I said, infinite horizon here is not included. In the scalar case, with one state variable only, in general, we get an ordinary differential equation. So in this case, it's easier to work with. And in fact, I think that much of the results I have here could be translated to this other context. But anyway, I focus for this work only on finite horizon game. Okay, at any moment you can ask me any question to stop me or so. Okay, so on. Okay, so the equilibrium can be characterized by three different partial differential equations, right? The classical one is the Hamilton-Jacobi-Bellman that is characterizes the value function, and then this focuses on the optimal return. A related partial differential equation that I call here the adjoint of co-state system characterizes directly the adjoint vectors, that is Osado prices. So this is used in several works, and what happens here is that we have a partial differential equation that is of quasi-linear type. So it happens that it's linear in the derivatives, but the coefficients could be non-linear, the coefficients that multiply to these derivatives. So has a less amount of non-linearity than the Hamilton-Jacobi-Bellman equation, but still is non-linear. Non-linear. And this characterizes to the derivatives of the value function. And other possibility is to work with the so-called Euler-Lagrange system that characterizes directly the equilibrium strategies. The structure is quite similar to the adjoint system. It's also a quasi-linear system of partial differential equations. So in this sense, share a lot of common properties. Here in this work, I work with the third approach. And why? Because in general, characterizing directly the equilibrium strategies allows to answer questions related with these strategies, qualitative behavior of the equilibrium. And then you don't need to pass through the derivative of the value function and then go back to the equilibrium strategy and so on. So I think it's a more direct approach. I'm sorry, because this is third. Okay. No, this is. Okay, I don't know how to go. Okay, I have to scroll. I have to scroll the screen. Okay. Okay, I think that because I am not showing the presentation in the right way, this is not a dynamic presentation, sorry. Okay. Okay, the Euler-Lagrange system. So how we can obtain a partial differential equation system that characterizes directly the equilibrium strategy? Okay, we can proceed as follows. Get the Hamilton-Jacobi-Bellman equation and then differentiate, applying the envelope theorem with respect to the state variable x. Use the first order condition. We are assuming here that the equilibrium is interior, right? So the first order necessary conditions is that the derivative of the Hamiltonian with respect to the controls are 0. So usually okay, this is not a general setting, but usually we have in the examples I am going to show you after, the first order condition is that the derivative of the utility function L prime I equals the derivative of the value function. This is in the resource games I am going to show you after. Then substituting this into the result of the envelope condition obtained from taking the derivative in the Hamilton-Jacobi-Bellman equation, then we get an equation where the value function doesn't play any role and only the equilibrium appears. I will show you more now in the equations. Okay, so what are the top objectives? Here is that working with this Euler-Lagrange system, try to get sufficient conditions of optimality for non-smooth solutions. So this is a difficult question because when we don't have smoothness, it's even difficult to say what is a solution of a partial differential equation if we cannot take derivatives. Then we use that very well-known concepts in mathematics, the notion of weak solution or integral solution. And this can be very general. So in fact, we need to narrow the class admissible so that the dynamical system has solutions and the maximization of the Hamiltonian is fulfilled, and so on. So here we have a modest approach in the sense that we work only with one-dimensional state variables. Okay, so the time horizon is finite, and finally the controls are interior. Okay, so we don't have any constraints other, for instance, than the non-negativity, but this is usually fulfilled in equilibrium. So we try to show a connection between this kind of games and the theory of quasi-linear hyperbolic systems that is very well known in applied math and in physics and so on. So in this context, we will analyze and we try to use in our results the concepts of weak and viscosity solutions, the Rankine-Hugoniot jump conditions that appear in physics, and in fact, this is key to show that the solutions are in fact Nash equilibrium of our vein, and some concepts like Riemann invariance that has a nice interpretation in our context. This is all from the mathematical theory of conservation laws. And I try here to apply to this framework. Okay, I don't know if you have any question up to now. Okay, okay. So the objective function, we write, okay, this is the payoff function that depends on the initial conditions, x, a state variable that is one-dimensional, and t, that is the time. Also, the set of strategies of its player is one-dimensional, right? This is the dynamics, the state variable. I call here the state variable g. In fact, the important variable is the x. The x is the initial value. And then, yeah, this state variable evolves along time according to this dynamics given by some f. Okay, but in order to distinguish the dynamics gt with f and the initial condition, I have chosen this notation. Okay, the dynamics depends on the state variable, the calendar, and the profile of the strategies chosen by the players. And this ji, the payoff function, is an integral payoff. We call this li. And we have at the end a terminal or residual value for the state variable. The admissible strategies are piecewise smooth. Okay, so they cannot be much general. For instance, I don't know, simply measurable, and so because we cannot manage then well the dynamical system. So this is it could be discontinuous, but has to be smooth on the regions, interior regions of discontinuity. And they are feedback controls, so they depends on the state variable and on time. Okay, I think I have chosen here to write GT first, but I think that in my next slides I use in the reverse T and GT. Sorry for this confusion in notation. So we assume that if we choose controls in the class calligraphy UI, then we get a unique and absolutely continuous solution of the dynamical system, and that the payoff function is continuous, at least with respect to the initial conditions. Then what we want to do now is to obtain necessary conditions for an interior and smooth Markov Perfect Nash Equilibrium. The equilibrium at the end, in some examples, maybe is not smooth, but this gives the possibility to construct a partial differential equation, and then from this partial differential equation that is only necessary for smooth solutions, we are trying to work to see if non-smooth solutions at the end are equilibrium strategies, that is, to establish sufficient conditions. So we first obtain necessary conditions for a smooth equilibrium, and analyzing this necessary condition, we give sufficient condition for non-smooth solutions. This is my point here. Okay, with interior strategies, the first order condition says that we maximize here this Hamiltonian. Okay, and then maximizing the Hamiltonian, we define the costed variable gamma I in this way. In fact, this is the condition of the first order condition. Taking the derivative here with respect to the controls, we get, after substituting, we get this expression. And then what we do is to derive in the Hamilton-Jacobi-Bellman equation with respect to the state variable, and use the envelope theorem to simplify things, and afterwards to substitute the costed variable, that is the partial derivative of the value function with respect to x, for this expression. And then we get this conservation loss system of equations, right? So this gamma is a function that depends only on x and t, the profile of the strategies. The Hamiltonian depends on the same thing, because we have already substituted the costed variable. And this is a consequence of taking derivatives in the Hamilton-Jacobi-Bellman equation. And this is written in conservative form, because this is a total differential. To obtain more analytical expressions, we need to perform the total derivation here and use the chain rule and so on. There is another way to find this equation that is by applying the maximum principle. Okay, but they are equivalent approaches. So once we have this necessary condition, then what we do is to say, okay, let's admit that we have non-smooth solutions. What is a non-smooth solution here in this context is a weak solution. Up to this end, what we do is to define solutions in the sense of distributions. That is, okay, sorry, this is a very bad selection of notation. This phi is not the control. Sorry for this. This is a, oh, no, this is okay. Sorry, this is okay, sorry, forgot this. The eta are the test functions, eta are the test functions. So what we do is the following. Okay, maybe phi doesn't have derivatives with respect to t or x. Okay, so this operation at the end is not allowed. Then what we do is to integrate with respect to t and with respect to x. And to bring the derivatives of phi to test functions that they are smooth and with compact support. So if we multiply integrating and using the integration by parts, that is typical in distribution theory, then we say that a phi is a solution of this equation if this happens, this double integral is 0 for every test function eta that we can choose. Okay. This is a solution in distributional sense. So in this way, we relax regularity. And moreover, if it happens that phi, the equilibrium strategy, is smooth, then if we turn back to the original formulation, then it happens that satisfies the conservation law as a classical solution. So the weak solution framework is necessary for us because we are working with piecewise smooth solutions or discontinuous Markov Perfect Nash Equilibrium. Okay, this is the definition of Nash equilibrium that we all know. This is sorry, I wanted to say that, in fact, this is one of the necessary conditions for being a Nash equilibrium. It is that the equilibrium is also an equilibrium of the static Hamiltonian game. That is, then we call this the Nash property of the Hamiltonian. This property is that this is the typical notation. If this is the equilibrium strategy, then this phi hat minus I is that the other players, with the exception of player I, play the equilibrium strategy. And then if the player I deviate from the equilibrium, then in the Hamiltonian has no incentive for deviations because it gets not more than playing the equilibrium. This Nash property is interesting. And in fact, it gives a rule to choose the correct solution of our equations. Because what happens now when we work with non-classical solutions and work with the concept of weak solution, then it can be many weak solutions, a lot of them. And some problems could be infinitely many. Then the problem is which solution to choose, which is the correct Nash equilibrium. And it is not because we have infinitely many Nash equilibrium. No, it's not the case. In fact, in general, with strong concavity, only one of the solutions is the correct one. And it happens that these conditions helps to isolate the good candidate. Okay, so this is the good candidate. So not every solution of our equations, if it is not classical, is going to satisfy this condition to be an equilibrium of the Hamiltonian game. So here, sufficient conditions for the Nash property. Okay, concavity, an interior solution, but I forgot to write here that this is true only for classical solutions. Okay, so if the solution is not classical, it has discontinuities, concavity, an interior solution is not enough to have this condition. Okay, so this is because the discontinuities then makes concavity. Concavity is not enough because if the Hamiltonian is concave, but you are evaluating along a curve that is discontinuous, then problems can arise. Okay, so what kind of discontinuities we allow in our solutions? This is a discontinuity manifold. Remember that we are in a scalar setting, so this is not very difficult to establish. If we have higher dimensional problems, this is rather difficult. We allow the discontinuities are formed by finitely many curves. This is that they are called DIL. And these curves are given implicitly in general by this equation through this expression. And then the discontinuities are admissible if it happens the following. So we define first the speed of propagation of the discontinuity. This is typical in the math theory of conservation laws. That is like applying the implicit function theorem here to obtain, if we want to solve x in terms of t, right? Applying the implicit function, we can have the derivative of x with respect to t. And in fact, this expression. This is what we call the speed of propagation. Okay, and then it's going to play an important role in what follows. Okay, so this has to be well defined to work with this kind of solutions. Okay, for the analysis, we require this to evaluate our function gamma I that we got from the first order necessary conditions. We evaluate at the state variable and the value of the equilibrium profile at the state variable. This is a path. Okay. Okay. And then this is the admissible solution we are going to work with. So a set of discontinuities and a weak solution of our system is admissible. It happens the following. The strategy phi is piecewise smooth, so we need some regularity, and it's an integral solution. It satisfies the Nash property, and the characteristics of the system are transversal to the singular set D. That is, the characteristics are given by the function f, that f defines the dynamics. And then the singular set D is given, the speed of the shock is given by these expressions. So what we allow is that they are not parallel, okay, but they are transverse to the discontinuity. So they are not. So the evolution of the state variable is not tangent to the discontinuity, but passes through other region of smoothness in a definite way. So this condition prevents the manifold from being a characteristic cube itself, ensuring a well-defined shock speed. This is typical in this context. And finally, another question is that the optimal state trajectory cannot intersect the singular state D in infinitely many points. We allow only for finitely many intersections. This is difficult to assure. So it depends in the model we are working with. I have not been able to find any result saying that with such and such hypothesis you have that the trajectory is going to be only with finitely many intersections with a singular set. It's a technically difficult question for me, at least, to solve. And this is the theorem, okay, that if we have an admissible pair of discontinuities and solutions and strategies, then it's a Markov Perfect Nash Equilibrium. And in fact, we can prove that outside the singular set, the value function is derivable, and the derivative with respect to x is given by the co-state function, so that from here we can get the value function by means of a quadrature, that is taking the integral with respect to x, and these functions, the it is a constant with respect to x, but can be characterized by means of the Hamilton-Jacobi-Riemann equation. For characterizing this GIT, we need the Hamilton-Jacobi-Riemann equation. Okay. Okay, as I said before, uniqueness here is a problem because a Cauchy problem for a conservation law often possesses many weak solutions. So we have to be able to give criteria for choosing the correct one for our game. And then our selection principle is that that this strategy has to satisfy that this has to be an equilibrium of the static Hamiltonian game. And predictability, I have given this name there, that is that we have a unique, well-defined trajectory for every initial state. So in fact, this theorem, the theorem before, is not complete in the sense that I haven't been able to establish conditions for the second part, for when a weak solution of the system gives well-behaved trajectories, and that only have intersection with the discontinuity manifold infinitely many times. Okay, let me solve the equations in a very simple game. That is the non-renewable resource game, where we have. Okay, I say here that we have a symmetric game, but at the end, in the last slides, I have an application to asymmetric game. Okay, but the resource dynamics is typical. So the players extract from the resource a rate UI. The resource is non-renewable. It's like oil or so, and this is the payoff. So the payoff for the players depends only on their own strategy. So they don't have any motives regarding the consumption of the players. Okay, and at the end they value the resource with the function SI. So the strategies are the Markov strategies, and the assumptions is that the running utility is typical, increasing, strictly concave, and classy tree, and satisfying in other conditions. That is at 0, the marginal utility is infinite. When consumption goes to infinity, the marginal utility is 0, and so on. In terminal value, we choose increasing, continuous. There is a typo there, continuous and piecewise function. So we allow here for the terminal value to be continuous, but it could be non-smooth, only piecewise smooth. We say that the game is symmetric if all the players share the same preferences for consumption, same terminal value, and same discount factor. In this case, and suppose that we look only for symmetric equilibrium. In this case, the partial differential equation system reduces to a single equation. Okay, so let me show you the equation and some solutions for a specific game in a very simple case is with null discount factor. So this is finite-horizon, so let us choose discount factor r equal to 0. In this case, the conservation law is given its way. So it's the partial derivative with respect to t of the marginal utility plus the derivative with respect to state variable of the Hamiltonian is 0. Here r is 0, I said before. This L prime is like the flux in this kind of equations. Sorry, is the density in this kind of equations for the analogy with physics. And the flux is what it depends how it moves with x. This is the Hamiltonian. That the Hamiltonian in this framework is in this way. No, sorry, this is wrong. This has to be a plus and this has to be a minus. So I have to correct this. A plus utility and a minus here. Okay, that is due to that the players are extracting resource. The terminal and boundary conditions are important. So the value of the strategies at the final time t is obtained from the maximum principle, okay, and it is that the marginal utility at S prime has to be equal to phi. This is from sorry, the marginal utility at phi at time t has to be equal to S prime. Okay, this is the maximum principle. And we have a boundary condition that is due to that we cannot consume if there is no resource. So when there is no resource remaining, then the consumption is zero. So we have a final condition and a boundary condition. I have chosen here, for illustration of the theory, a terminal value function Sx that is non-concave. In fact, this is convex and piecewise linear. So we know that when in presence of non-concavities, in general, the problem becomes bad behavior. In fact, we can have discontinuous solutions and so on. In this case, I have chosen terminal value is Ax up to some threshold x bar, and from here is another linear function, and I have chosen A smaller than B, so that the slope in the first region is smaller than the slope in the second one, so in fact the function is convex. And this convexity implies that the solution is not going to be smooth. However, in this kind of problems, if we choose with some care the terminal function concave, in general, we are going to have very, very well behaved solutions, but it's not the case now. Okay, this discontinuity on the marginal terminal value function defines two critical levels, because this is linear, it's piecewise linear, that we call alpha and beta, given in this way. So in fact, this is alpha is going to be the value that the equilibrium strategy takes when the resource x is between 0 and x bar, and we are at the end of the game. No, this is, sorry, I'm going to go back here. It's because of this definition. This phi, okay, is the inverse of the derivative of L in S prime. So the value at t of the equilibrium is this expression that I call alpha and I call here beta. Because A is smaller than B and L prime is decreasing, then we have that alpha is greater than beta. Okay. Okay, I didn't show here the Rankine-Hugoniot jump conditions because I was thinking I didn't have time enough. But using these jump conditions, this is well known in mathematics. Okay? The unique, what they call entropy weak solution. Entropy means, this is also a concept that comes from physics, is that is the solution such that the characteristics of the equation doesn't go that is collapse or converge to the shock line, not in the reverse, that from the shock line they depart, because this has to do with irreversibility of the physical processes. And it happens that this solution, the entropy solution, is also the good solution in our context. It satisfies the Hamiltonian maximization. It satisfies that there is a good solution for the trajectories and so on. This is so basically in this, at least in this example, I simply have to choose the solution and to check that everything works well. In this case, I don't know. Maybe it's not maybe it's the rule, but I didn't check. So, and this is the solution, the good solution. Here, let me explain. This is the alpha. I'm going now to show you a graph that everything is going to be clear. So alpha is the value. So this is a constant value for the equilibrium strategy when the resource x is between these two lines that depends on t. This is a region of constant consumption. And there is another region of constant consumption with the level of the resource that remain to extract is greater than this capacity. I'm going to show you. This is another constant consumption. And there is also a region, not so broad, it's not constant consumption, but it's given in this way. It's the inverse of this function that is defined at the bottom of the slide. At x divided t big T minus T. When the resource is small, that is when we are near extinction of the resource is going to be 0, then in fact, the equilibrium strategy that applies is this expression. Here they are the definition of the previous symbols. KT, this capacity is the shock. The shock is the line or curve that separates two lines of discontinuity. And here is the discontinuity because phi here jumps from alpha to beta. So this is the shock. And it's given in this way here is a line with this coefficient, okay, and the threshold that defines the terminal value function, the terminal function, and this calligraphic epsilon u is the elasticity of intertemporal substitution. That depends on the payoff of the players. So no, epsilon u defined here. No, is epsilon u. No, it's the absolute risk-seeking index, no? Absolute risk-seeking index of the players. Yeah, and divided by u is the marginal interval substitution. Yeah, right. Okay. So, so in fact, this has some economic implications because whether a solution of this kind exists or no depends on the degree of risk aversion of the players. For instance, I need this condition. So here this means, this is what is here at the right bottom, that epsilon u divided by u has to be smaller than n divided n minus 1. N is the number of players. So for instance, with n is 2, this ratio has to be smaller than 2. If n is 3, smaller than 3 divided by 2, and so on. And in fact, notice that this is more and more strict as the number of players grows. Okay, and this means that the players are more and more risk averse. Okay, need to be more and more risk averse as the number of players increases. Because if this condition is not fulfilled, this solution is not valid, and I don't know which is the solution. In fact, with the other, if this is not fulfilled, I don't know which is the solution. I have not been able to find it. So this means that for having this kind of solutions, we need some important amount of risk aversion in the players. And of course, the number of players also plays a role. For instance, if we are in the control game, there is only a single player. In fact, this is not a constraint at all because this is infinity. So this happens, this worked well for single players, for the single player game, okay, without restriction in risk aversion. Okay, this is the regions. So here in the horizontal line, we have the stock, the resource stock, and in the vertical line, we have time, reversal time, because so that we have here in the horizontal axis, there we have the initial condition. Here, the equilibrium has to have the value alpha, here the value beta, and then what is here in this cone below the red line is a constant region. Here, the equilibrium takes the value of beta constantly. This is the shock. And here, in this other region between the blue and the red line, we have a second region where the phi is also constant, alpha. So we have a line of discontinuity here. And then we have another interesting region, region 1, where the equilibrium is given in this way. And this is the line that separates these two regions. Across this line, the blue line, the phi is continuous. So here is not smooth, but it's continuous. Okay, so this is the stack of this solution. And I have now an asymmetric game, not a symmetric one, an asymmetric game with hyperbolic absolute risk aversion utilities in this kind. Here is gamma I, sorry, gamma I, smaller one. Also a linear terminal value, but this is not non-smooth. This is linear, without more problems. And I suppose the following assumption of the parameters, that the product of the risk aversion parameter of the places is greater than 1,4. So we need, as before, we need that the risk aversion of the players are not small. For instance, this for this kind of problems, when there is a version where the eigen tends to be neutral, so I have been not able to find solutions. Okay, and gamma 1 plus gamma 2 has to be also greater than 1, and this is for assuring strict hyperbolicity of the system. That is a concept that comes from math, and that is needed for getting this kind of solutions. And I have imposed here, because this is only an example, this condition, okay, that the parameters theta 1 and theta 2 are given this way. It's like the alpha beta before, okay, that comes from these coefficients, that the marginal utility at the final time of players has to be equal to the derivative of the terminal value function, in this case to alpha I. And then I impose this condition. Of course, this limits a lot the application of this game, because, but this is to obtain here, in this case, clean solutions. Because working with, as we have now asymmetry and two different players, working with discontinuities here is difficult. I need to study more in this kind of games. So I impose this, that is going to ensure continuity of the solution, but non-smoothness. Okay, this is the conservation law for this game. This is the quasi-linear structure. We have that the partial derivatives are linear, but they are multiplied by non-constant terms, that in fact depends on the solution. For this reason, it's quasi-linear. And they are here the boundary conditions. When there is no resource, of course, the destruction is 0. And at the final time, because I am using here reversal time, at time big T is 0. Now, it's tau is equal to 0. Then this is the boundary condition at the final time, because we are imposing linear terminal values. Okay, this is a very nice and elegant solution that depends on eigenvalues and eigenvectors. If I pick the matrix from the row system, let me go up to the this is the system, right? So in fact, it's linear in derivatives. So picking the matrix is this. This is the matrix. It's not non-symmetric. And the eigenvalues are easily computable, are given in this way. Gamma 1 and gamma 2 are the parameters of risk aversion. And the solution uses the right eigenvectors. That is also, and they are also easily computable, and they are these expressions. I have chosen this representant. Okay, and then the solutions consist of constant states and what is called centered rarefaction waves. And a centered rarefaction wave is constructed as follows. Consider this Cauchy problem here. This I have chosen instead of U, C. So we have a system of the ordinary differential equations that are given. The parameter is not time now, it's sigma to distinguish. And here R1 is the positive eigenvalue, that is with plus and plus here. Then suppose we solve this Cauchy problem with initial condition 0, 0. To this solution, to this Cauchy problem, we call big R1 sigma of 0, 0, because it starts at 0, 0. And then suppose that we are able to show that for some sigma bar, 0, 0 is connected with theta 1, theta 2. I remember theta 1, theta 2. Sorry, I'm going up. Theta 1, theta 2 was given here. Okay, and depends on the values alpha I, the marginal value of the terminal value of the terminal function. Sorry. Then this means that we can connect 0, 0 and theta 1, theta 2, the two constant states, via a rarefaction wave. Okay. Okay, this is possible in this problem. Why? Because I have imposed the correct assumptions. Okay, and then this sigma bar is given in this way. And this is the same value as this because I have chosen that. Otherwise, this construction is not possible. It's no longer possible. What is the rarefaction wave? The rarefaction wave, this is a pure theory, okay, is given in this fashion. In fact, the solution E1 and E2 is exactly equal to this, to the solution of our previous ordinary differential equation. And sigma satisfies this condition. Okay, this is theory. I have copy for a textbook, okay, and apply it here. Okay, so because I am been able to compute everything here, I have a very nice solution. Okay, the solution in fact is this one. We have a constant state that is given by the final condition when the resource stock is large enough. Depends on these parameters that involves the risk aversion parameters of the players and the alpha 1 and alpha 2. And in the other region, when x is getting smaller and smaller, the resource stock is given in this way. It's linear in x. Okay. And I want to show you here the trajectories that this equilibrium. Okay. I forgot to say that this qualifies as an equilibrium, even it is not smooth, because I can apply my previous theorem, and in this case, it's easy to prove that the conditions. In this case, even the solution is not. It's continuous. It's continuous. So in fact, I don't care here for the discontinuity region because this is continuous, and there is a well-defined trajectory. The trajectory, in fact, can be computed exactly. In region 1, if we start in region 1, that is the initial resource stock divided by the time is great enough, is large enough. Then we have, because we are in the constant state, we have this trajectory. In region 2, we have a combination of constant and the wave solution. So this for intermediate values of the ratio x0 over t. And finally, if this we have a very small amount of resource or big T, then we have this other solution. It depends on here tau is reversal time. Let me show you this graphical illustration. So here, this is the region 1 is a constant state. And here so here the players consume at a constant rate. So the solution here is linear, is decreasing, linearly decreasing. And in fact, there is no extinction here. Always when we start in this region, we don't have the resource doesn't exhaust. So this region is for when we have that the resource stock is very large, and here is x, for instance. This is a trajectory obtained with 10 in arbitrary units of the resource stock, okay? And the time horizon is 2. So in fact here, 2 is relatively small with a very large amount of the stock we have. So in fact, there is no time to consume everything. Of course, it depends on the risk aversion parameters of the players and also on the alphas, but this is a simulation. I'm going to show you now the table for this simulation. Now, if we are in region 2, this is an intermediate state. So in the sense that we have, the resource stock at the beginning is 10, and we have the time horizon is also 10. So in this case, we start with a constant consumption, so we decrease constantly, and here we reach region 3, where now X has decreased into this level, and then the consumption is not constant any longer. And in fact, the trajectory goes to 0 smoothly, and in the limit at time big T, the solution, the resource is extinct. In region 3 is that we don't have any region of constant consumption because we have here a relatively small quantity of resource in a long time to extract the resource. So in this case, we converge to 0, also to 0, but in an exponential way. This is an exponential convergence. Okay, okay, I have done these simulations with these parameters. For instance, I have chosen for player 1 risk aversion 1/2, player 2 2/3. They satisfy all the conditions that are here. Global indicators, I mean, the risk aversion has to be greater than 1, the product has to be greater than 1/4. This has to be fulfilled, and for this choice, I have chosen here that the marginal resource valuation has these values, completely arbitrary, but for fulfilling this condition. And then the constant consumption near the boundary, near the final time, is computed as 1.5 for the first player, 1.125 for the second player. Okay, and this is the region. Sorry, this is the line. Sorry. Oh, this is the line here. This dashed line. This is the line that separates extinction, that is region 1 and 2, from non-extinction in this game. Of course, this line moves with the parameters, with risk aversion. Risk aversion has a great impact in this line. Okay. So, and this is everything about the illustration, and this is the conclusions. So we try to give a framework for characterizing discontinuous and piecewise smooth equilibrium in a restricted class of non-cooperative differential games, because I need scalar games and the interior equilibrium. I have tried to show that the Euler-Lagrange system with all the apparatus from math, that is Rankine-Hugoniot jump conditions, eigenvalues, eigenvectors, waves, and so on, they can be useful for trying to solve these kind of problems. This provides also a method to construct the value function by a simple quadrature. Okay. And in future research, I need to explore in more detail uniqueness criteria that are economically sound, to extend the analysis to higher dimensions, and yeah, maybe to use this approach in stochastic games and use elements of viscosity solution theory, and give more specific applications to real-world economic models. There are some references about the Hamilton-Jacobi-Bellman equation system on shadow prices. That is the shadow price system, the other approach. There is a very famous paper by Shunichi Susui and Kazuo Mino that used the shadow price system, but for finite-horizon game. And regarding the Euler-Lagrange system, there is a paper that is very interesting. It's quite old from my point of view. That is by Chen and Rustichini, that they study a linear quadratic game with this the same equation like I am showing you. And this was previous to my paper with Julián Martínez and Guiomar. We were thinking that we were the first to use this kind of approach here, but in fact, I found this other paper by Chen and Rustichini 10 years before. Okay, and this is all my presentation.